morning, dear JE aspirants. Today we are going to see a very important topic in isomerism known as Tautomerism. It is a very important topic in the list of isomerisms we have seen, especially in non-optical, non-geometrical type of isomerisms. So now we are not just going to learn up with some any random examples. Today we are going to learn Cengage level with Cengage level examples solved and showed to you. Okay. Now come, let's start the class. So what exactly is this tautomerism? It is very simple. It is a type of isomerism where the nuclei of any random atom of any one of this molecule shifts its place from one to another. That is known as tautomerism. And not always it is an atom, it is mostly a nuclei, which means electron is not considered over here. Electron can come or may not come, but the nuclei is the one that we have to see. Okay, so first let me take a Cengage book first example itself, this one. So how exactly is this tautomerism visible in the sense? Let's see here. See, there is some conjugation present here, double bond, single bond, double bond, and we all know how this pi bond is forming due to hybridization. Here we have an any one of the axis overlap of carbon and carbon, and we have another axis. Example, let's consider this z axis and x axis, and there will be little bit inter attractions over here, but they just cannot collide to each other because there's a sigma bond formed over here and they are distant, as we know in the hybridization concept. So now what happens, as this bond is now entirely very weak, as pi bonds are very entirely weak, they tend to move from place to place. So what happens, this pi bond can get transferred to the next position, which means this can also result in CH2 single bond, and here it forms an ion CH2 plus. So the nuclei of one of the hydrogen is the one that moves here and there, forms a CH, double bond CH, single bond CH, and now here the pi bond from this one went to here, so it attained a positive charge. And now here see, this pi bond goes to this part, no, so this carbon atom, no. So when it goes like that, this gets a negative charge, right? So see, that nuclei of one of the hydrogen is started to move. It was once here and then went here, which one other one which was here went to here. See, there is a chain like reaction, right? From this it turned on, went to this, positive, negative, and due to the conjugation it travels. Understood? Yes. And these are the main topics we are going to cover today. We are not going to cover entirety of tautomerism base to base. This is a rapid like I guess around 30-minute revision today. So next we are going to see directly, let's move on to any rather than any jargon. Let's now move on to another important part, which is what are the types of generally tautomerism. And one of them are triad and dyad. Dyad is the example that I showed you earlier. One hydrogen moves to the adjacent hydrogen atom in the conjugation chain. Now let's see this triad. What exactly is this triad? As the name mentions itself, triad system means it moves on, the hydrogen from the first position goes to the third position. Let me now write down you an example from Cengage book itself, which is C double bond O, single bond C, single bond H, and H hydrogen. Yeah, this happens. So now see what is happening over here now. So now let's take one example from Cengage book itself, which is C double bond O, single bond C, hydrogen, this. Now what can this turn into during tautomerism? Let us see now. Okay, now what happens, oxygen is highly electronegativity and pi bond is very weak, so it attains a partial negative charge, right? So due to that, what happens, this thing get a partial positive charge, and there is this hydrogen, right? this hydrogen now moves to this, and as this is pulling, this pi bond is there, right? This thing goes to here, so that this oxygen from partial negative to full negative it attains. And now from partial positive to full positive it attains, right? It has to be diluted. So there is a positive charge, and in order to fulfill that positive charge, what happens? This hydrogen moves here. So now let's look at the result. See, single bond OH. Why? Because already one of the pi bond has traveled over there, right? So that is why now the single bond is occurring, and the nuclei has went from here over here. See, there's a triad system. 1, 2, 3. The hydrogen from the first position went to second position and to third position. 1, 2, 3. See, or else you can also take this one also. 1. You can't take this one. Why? Because it has to travel 4 position. But this 1, 2, 3. Simple as that. Now let's see the next one. Now then it will turn into double bond as hydrogen went over here to fulfill this positive charge. So what happens? See, double bond C arises and one hydrogen exists, and we can bond anything. And yeah, see, one thing can bond over here as carbon can have 4 different bonds. See, you've got tautomerism. Now let's move on to the next one. Now as we saw how the triad system occurred, we are now going to apply the same thing to this compound, which is acetaldehyde, as we know it already. So now let's think what it can possibly do. So now this we can see, right? C double bond O, the same thing that we already saw in the triad example. And so what happened here? Partial negative, partial positive, right? Due to that, this electron of the pi bond goes to there, attains negative charge, attains positive charge, and afterward let's see what happens over now here. Now what happens? Due to this, there is a triad system forming, this to this, right? So now one hydrogen goes to this side, as there is one electron, there should also go one nuclei in order to make the stable, this O minus stable, right? So now for that, this turns into CH2, okay, and here C plus over here, and we will have a single bond over here now, OH formed, double bond here, and hydrogen. Why double bond? We already know it, only the nuclei went over there, right? So there is still one electron, still one electron pair over there. So if you want, yeah, we can also keep it like this, negative. And now there is an electron deficient carbon over there, right? So what happens? This negative charge, there is this one lone pair, right? This can go over here to bond, right? So now what can you give? CH2 double bond C, single bond OH, single bond H. Let me explain again how exactly we got it. C double bond O. Okay, highly electronegative. So what happens? Partial negative arises. So if partial negative arises, here partial positive arises. So now now there is a partial positive charge over here, right? So now then what happens? Due to this electron pair moves over there, right? So now what happens? CH2 single bond C, single bond O minus plus. It can form double bond but from that is when we have come. This is, let me remind you again, this is not end product. This is just the mechanism of how it is happening. So for that is why I wrote. But this is not formed by acetaldehyde. The final product is only formed. This is just the mechanism. So now there is one electron pair there, right? So if you give one nuclei to it, this electron can now definitely form one hydrogen, right? So there is CH3, sorry. So this CH3 can donate one hydrogen over here, right? One of the hydrogen nuclei over there. So that gives us CH2 minus, because it only gives the nuclei, not the electron pair. So CH2 single bond C plus single bond OH. This one goes to here using the triad system we already saw here as the second concept. single bond H. So now see here, there is a negative charge and positive charge, which means they can form a bond, right? So they do it, which gives us CH2 double bond C, single bond OH, single bond H. See, and what is this? This is vinyl alcohol. Spelling might be wrong, don't care. Just see vinyl alcohol acetaldehyde. See, this is the mechanism. Partial negative, partial positive, electron goes over here. Due to that, one hydrogen nuclei moves over there due to triad system, and there is a negative charge, positive charge, and negative and positive form a double bond, gives rise to vinyl alcohol. This is our ketone to enol conversion. See here, ketone group and enol group. One converts into another one converts into this. Ketone turns into enol. See, this is aldehyde group, COH. But look at this part alone. Just forget all of these. C double bond O. Only that one now we are seeing here. Okay. So this is ketone to enol conversion. Go. So now let's look at the next concept, which is the solvation effect of enol and ketone, and how exactly the solvation occurs. So first, before this, we have to see about the stability, how it is attaining stability, how much percentage of enol content is there, and things like that. So first I took one example here, which is acetyl ether. So now let's apply tautomerism to this. Let's see, can it form tautomerism? Now, okay, let's see here. Same mechanism as earlier, no different. Partial negative, partial positive, right? So pi bond goes over here. So partial negative turns to full negative, partial positive to full positive. So, and this pi bond disappears. Exactly, right? So now next what happens? Triad system is here. Right? There's a triad system formed over here, right? See, 1, 2, 3. And positive, negative. Perfect conditions for a triad system to form. So one hydrogen nuclei specifically travels along the triad system and donates one hydrogen nuclei alone to over there. So now what does that form? That gives us an OH, and here it gives us one CH minus. So now what happens? Positive, negative. They can now form a bond over here, right? Double bond. So charges disappear, double bond forms. This is a 5-membered ring. But where is the ring over here? There is no ring over here. No, there is a ring. How? This can form an hydrogen bond. So this forms an 5-membered hydrogen ring. And so this thing is more stable compared to the ketone. So generally ketone is less stable. Ketone is more stable because C double bond O bonds are very stable generally. So that is why ketone is generally more than enol in stability orders. Okay. So see, ketone is generally higher than enol. But now here this ring has formed over here, right? So then there is no double bond. But due to this ring, even though there is no double bond over here, it is more stable because it is now forming a ring. So that is why this thing has more percentage. Generally, if you see the before compounds we gave, there will be mostly ketone will be like 93%, enol content will be around 3% or 7%. But in places like this, it can be more than 50, 70 or 80. And it depends on what group we are putting over here or over here. Why? Because if this thing is, and the difference is that now this thing can support more than 50% of enol content. But if I shift one small thing, if now I put this substituent over there, this thing this percentage of enol won't be more than 50 but less than 50, which is around 26%. Why is that difference coming over there and here? Because the difference in both of them on how good they withdraw their electrons. So that is the reason why even rings stabilize it, even though the ring stabilizes it, due to see this thing and CH3, the difference in how much powerfully they withdraw the electrons, the electron withdrawing capability, due to that difference the stability of the entire compound changes. So due to that, if OET is present, the stability drops, so enol percentage also drops. If CH3 is there, the stability also increases, so enol percentage also increases. So but now why am I telling this for solvation effect? See, for example, let's assume our before compound itself. Go. See, now we have attained to the previous compound we had, which is acetyl ethyl. So now we are for example, we are mixing this with H2O, a polar solvent. So now this thing can split into ions, right? H plus ion and OH minus ions. Now what happens in this sense? See, do you remember when this thing became O minus and C plus? And we used the triad system to transport the nuclei of the hydrogen to over here, in order to satisfy and make this more neutral, right? More stable, right? But now what happens? See, now there is an abundance of H plus ion. See, H plus ion, H plus ion, H plus ion, as this is in water, as we mixed it with water. Everywhere there is H plus ion, only there is this compound in middle. So before even triad system can activate, as there are free H plus ions, it directly bonds over here. So then why is the use of triad system forming? So what happens? Enol can never form, because now, for example, you might ask me, okay, considering your reasoning, OH can appear, right? Then COH there, right? Why not enol? Why? Because see here, there is one hydrogen over here, there's a C plus ion, and nothing can satisfy it. And you might say, okay, put one electron pair as you did in Tautomerism, that thing. If you put one electron pair over here, this attains a positive charge. See, the reason why at that time we didn't attain a positive charge is because a nuclei was already donated and there was a negative charge over here. But if you are now forcing a neutral atom to give a double bond and become unstable, it won't. So this entire compound is very unstable, so it cannot even exist. So now it has a junction in it. Enol also cannot be formed, and H plus and free H plus ions also now cannot bond up with the oxygen to form any stable compounds. And there is only now one type of stable compound that can exist, which is our previous ketone compound itself. This is the only compound in all of these three cases which can remain stable, right? So yeah, this is the only compound which can exist. So what can we observe? What can we say as a result from this? Which means when polar solvent increases, that to polar protic, because only polar protic solvents can give you an H plus ion. So when polar protic solvent is there, arrow decreases, then enol content decreases, because this polar protic solvents H plus ion doesn't even enable the possibility of an enol compound. That's the reason in solvation, when you mix any ketonic compound or tautomeric compound which has an enol to ketone movement, if you add it inside a polar protic solvent, enol concentration will always be less and ketone concentration will be high. I'm not telling they won't even form entirely. They will form, but very trace amounts, like 2% or 3% in many cases. So that is our solvation effect of enol. Next we will move to mechanism. Now let us see mechanisms. So there are totally two type of mechanism, which is acid catalyst and base catalyst type of reactions. This one in top is acid catalyst and bottom one is base catalyst over here. So let me walk you through how exactly it happens. So now for example, let's take this hydrocarbon with oxygen as its substituent, and now let's apply the same Tautomerism rule. Now what happens? Now here negative charge erases, right? Partial negative, partial positive. pi bond goes over here, full negative, full positive. This is the basic Tautomerism rule, right? Now after here O minus happens, right? So now look at this. There is one hydrogen over there, right? This hydrogen goes and bonds up with this, okay? So when hydrogen goes and bonds up, it forms OH. Pi bond disappears because that is the one that turned into the O minus. And see here. Now here it is CH2, right? In this place. In dash line reactions, we know that in this place it is CH2, right? In the CH2, one hydrogen alone I am splitting and keeping over here, and you will know soon why. See, now there is this positive and there is this hydrogen over there, right? So now what happens in this sense? This hydrogen moves on and goes over here. See, this hydrogen, let it be as such. There is this water medium. Inside the water medium, there is this H plus ion concentration, right? H plus ion will be there as it is an protic solvent and polar protic solvent. H plus ions will be there, and that now goes and fulfills this place with this hydrogen over there. So when this hydrogen goes and forms over here, it forms the double bond, and there will be a deficiency, right? Because it is not any minus, and it's not CH2 minus, right? So as it comes here, there is a positive charge over here, deficiency, right? So the deficiency of hydrogen will be now taken care of this H plus ion, which results in this stable structure with a double bond. Now from an ketone form, we have traveled all the way to an enol form without any disturbance, and both of them are stable over here. So now let's move on to the base catalyst reaction. See, I had to tell you one thing. So tautomerism only exists when there is an alpha hydrogen over here. And see here, we can find this as an alpha carbon. So these two both will be considered as an alpha hydrogen, right? So now let us see. So there is an OH minus ion concentration in the same water, right? So both of the cases we are adding the ketone groups with the polar protic solvent. So here H plus ion comes, here OH ion comes. So this OH ion comes and bonds up with any one of these two hydrogens over here. For example, let me say this bonds with this hydrogen. As this is a covalent bond, this has one electron, this has one electron. But this OH minus ion attracts us more stronger than this carbon. So this hydrogen bonds up with this OH minus to form H2O, and the formed H2O is removed out of the game. So now what happens? Negative charge arises due to the loss of an hydrogen, right? So that is what has happened over here. If you see, negative charge arises, that hydrogen is still over there, but now present as H2. The reason why we have written both of the hydrogens is to show that it can bond with any one of them, not only one. So now what happens afterwards? Now tautomerism occurs. What happens? Partial negative, partial positive, pi bond goes over here, full negative, full positive, pi bond disappears, and what happens? And now one of the hydrogen over here moves out to this oxygen as to triad, but it will go, but not now. So now there is one negative, right? Generally we will start with the hydrogen to put over here, but this case we will stop. Why? Because why not go with the triad? Why not just bind up with why not go with the triad in the sense like normal tautomerism? There is one small difference over here. Why? Because this entire thing is in a medium of a polar protic solvent of H2O, which has now been split into ions of OH minus and H plus ions. So, and H plus ion can come and bond over here. Not always triad has to occur. So that is the reason why, rather than having the concentration on making the triad rule, it just waits. So what happens? Due to the presence of H plus ions, it later binds up with it. But for now, in order to make this place stable, because see, minus ion, very unstable region, right? The central region. So this minus ion, this plus ion form a double bond over here, but still the O will be negative. O minus ion will be still present with. So there is still this O minus ion over here, which is not changed now. Now here comes the acids, a polar protic solvent of H2O. H plus ions are also there, right? Now as it has already formed a double bond, and this random H plus ion from the medium comes and binds up with this O minus to form this stable compound of containing the enol group in it. So again, from ketone group we have into enol group. Same over here, from ketone to enol. So this is the mechanism of tautomerism. So now let's go to the final topic of today's class, which is nitrogen containing compounds which exhibit tautomerism. So there is a total of around 6 to 7 total type of compounds which contain nitrogen and parallelly exhibit tautomerism. But today now I am going to tell 3 of the most important one alone. And first one we are going to see nitro and isonitro. See, just looking at the name and the compound, you have immediately realized how exactly this thing is there. See, this is a nitro compound, this is an isonitro compound. From the charges itself, you would have guessed it by this time. So, how exactly this happens? This entire part is very easy. It is just flipping of double bonds and single bonds and H plus nuclei. That's all. So, see. Generally, we start up with an partial negative to partial positive, right? This time, let's skip all of them. We just know it already. Partial negative, partial negative. Partial negative can arise over here. Partial positive and can also arise over here, right? So now basically what happens? This thing takes it, right? So full negative happens. And when hydrogen from the surrounding bonds up to form OH. One compound we have already exist. One compound is now existing. This plus won't come. And now see, from this, using the triad rule, which is the second topic itself, one of the nuclei of hydrogen in CH3 goes over here and comes over here, right? And by the time this thing contains a negative charge and this thing contains a positive charge over here, right? This negative, this positive forms a double bond. Same reaction, only difference except of carbon, here nitrogen. Same, right? And now see it. Enamine and ketamine. So this, by looking also the same thing. This is an enamine, this is ketamine. So looking at this, we already found it out already. So now let's do the same thing again. This time we have carbon itself over here. But looking at carbon and nitrogen is comparatively more electronegative. So this attains partial negative, partial positive. Okay, sorry. It originates. So as I said, it originates in partial negative, partial positive charge over here. But now this thing cannot attract from here because there is no double bond over here, right? So now rather what happens is that the next nearest double bond is this one, right? So it starts attracting from this thing slowly. It takes up the it takes up the double bond. See, from the double bond part, it turned into a single bond part. But now suddenly there is now 2 hydrogens here, one, and here now it's an already deficient. Again now this turns into one partial positive, right? Now it has to be satisfied also, right? So in order for it to be satisfied, now this thing donates one of its hydrogen nuclei towards it. So from this already gave electron and it already had the nuclei. This thing got it, and the same thing applies here. Same thing, instead of nitrogen here, it happens for oxygen. So what happens? An electron pair from there goes over here to form the CH2 plus in order to CH3. A nuclei travels over here, not an electron, and now due to it, and has already sent an electron pair with the double bond. This is stable. And if you see one thing, both of these examples, nitroso as well as isonitroso, and this and enamine and ketamine, both of them are examples for same type of nitrogen containing compounds. So you can use the same logic for this one for nitroso and isonitroso also. So this is the complete quick recap, the most fastest possible revision for tautomerism for JEE mains and advanced. Thank you.